So it turns out that these results do generalize a little bit. It's actually possible to drive the risk of the nearest neighbor classifier exactly towards the base risk if you increase the size of the neighborhood. One generalization of the theorem that we established is one in which you assign k nearest neighbors, you take a majority vote, and in that case you can show that the upper bound, instead of just being 2, is actually 1 plus square root of 2 over k. And as k gets large, it goes to 1, so you will be able to upper bound the risk of your nearest neighbor by the base risk. Another thing that's interesting that people have studied in great detail is a notion of consistency. And specifically, if you have a classifier, you say that it's consistent if you can show that if you take the average value of the risk of your classifier over many possible data sets, then it has to go towards the best risk, the risk of the base classifier, the base risk. And it turns out that there's a famous theorem in learning that says that as n goes to infinity, and if the number of nearest neighbors goes to infinity as well in such a way that the ratio of nearest neighbors to the number of points in your dataset goes to 0, then your nearest neighbor classifier is always consistent. I'm not going to prove that. One thing that these results leave completely open is that in practice, you don't get to take k and n to go to infinity because you're given a fixed n. And there is a fixed value of k, as we've seen in the notebook simulation, that gives you the best possible generalization risk. And choosing k is a problem of model selection, and we will go back to it when we talk about model selection and cross-validation. One thing I want to highlight, if you remember my remark, that when you're using one nearest neighbor, if you look at the empirical risk, the value is always 0. This suggests that if you want to optimize the value of k, you should not optimize k by trying to minimize the empirical risk. Because in that specific case, here for our nearest neighbor classifier, in your data set, the nearest neighbor of a point in your data set is always itself, because it's in the data set, and your empirical risk will always be 0. But that's a terrible choice to choose k, because it will always tell you to use one nearest neighbor, and simulations suggest that this is not the best thing. So one has to be very careful. K here plays the role of what's called an hyperparameter in your model, which is something that you have to choose using a much more principled method, and we'll talk about cross-validation later on this course. So to conclude on nearest neighbor classifiers, the result that we sort of established, and more details are available in the notes, is that the nearest neighbor classifier for k large enough will do just as well as the best other classifier out there, which is the base classifier. So it would suggest that all we have to do in learning is use nearest neighbor. But the trick here is that that result only holds if you have enough samples. And there are many situations where you do not have enough samples. Even if you're doing deep learning based on the image dataset called ImageNet, it only contains a finite number of images, and it might be very hard to acquire more. And therefore, practical learning considerations operate with a fixed size data set, and taking the limits as n goes to infinity, that's interesting from a theoretical perspective, but it's not super useful from a practical one. Second, the choice of k matters a lot if you operate with a finite data set, and we'll revisit that using cross-validation later down this lecture. Finally, there are some computational considerations that I'm completely passing under the rug in this class. One of them is that if I give you a data set with 1,000,000 points, finding the nearest neighbor might not be that simple. That could be very computationally hard. There are tons of tricks that you can use from computer science, such as constructing what's called KD trees, which are essentially trees to represent the points that you have in your data set. That will make it manageable, but it's still very expensive, and as the dimension grows, these things get very inefficient. So as a result, k-nearest neighbors are kind of cool, because in principle, they should do just as well as the base classifier if the number of points gets large. But in practice, you need to make a lot of assumptions to make that work. And so what to do in practice? Well, the trick is you have to start constraining your models a bit more. And what we're going to see in the next few lectures is that you can build classifiers that are actually quite effective by constraining the form of the probabilities px, py given x, and using them to estimate what they are, and using them as plug-in estimates for your base classifier.